Thanks, everyone. I know 15 minutes feels like 2 minutes when it's break time, so I appreciate your coming back promptly. Yeah. So this is now we're about to dive into our first session focused on the hypotheses of why marine survival is a problem. This will be fun. Our first session is called Focus on the Fish, analyzing salmon and steelhead individual and population characteristics to determine where and when survival is most effective, how their characteristics may affect survival, and whether their freshwater experience is affecting survival in the marine environment. So, enough to keep us busy. And for the next hour, we will hear from our panelists who are coming up to the front. I would like to introduce Zimmerman and Ken Warheit of Department of Fish and Wildlife from Washington Department of Fish and Wildlife, Greene and Chamberlin in NOAA Fisheries, Beauchamp of the United States Geological Survey you've seen earlier this morning, Michael Smith of Long River King, Beamish, retired from the Canadian Department of Fisheries and Oceans, Ruston of the Department of Fisheries and Oceans, and Erin Rechisky of Kintama Research. So thanks very much, you guys. I think Mara is first. Is that right? Yes, Mara and Correigh are first.
Yeah, Mara, I have you.
All right. Okay. Let's see. That's good. Okay, so Correigh and I are going to split this presentation in half. But the hypothesis that we were examining was that marine survival does a better job than freshwater survival in explaining productivity trends of salmon and steelhead in the Salish Sea. And this is sort of a foundational question, right, if we're going after what's wrong with marine survival and how is it affecting adult returns. We'd really like to know the relative contributions of the freshwater environment and the marine environment to the adult returns. So I'm going to start with a couple points that sort of form the background of how we examined this hypothesis. And first is to define productivity, which is defined in many different ways depending on what part of a community or fishery or population you're studying. And so we're defining it as the spawner recruit per parent spawner. And to look at this question of productivity, then we're partitioning our understanding into survival in the freshwater environment and survival in the marine environment, and that is partitioned largely by where we actually monitor these fish, which is at the lower end of the river in a smoke trap, and then back on the spawning ground as parent spawners. One really important note, earlier it was made a comment about how we're actually defining smolt to adult survival. The calculations for marine survival can vary widely, and as we started reviewing this in the literature, it's a really important point to make. Are we talking about marine survival before fish enter the fishery or after the fish enter the fishery? And if we're trying to compare numbers, it's really important that we redefine print in terms of the percentages and the numbers that we're actually looking at. Survival in both environments, freshwater and marine, varies widely among the years. We did provide a short review of this in the plan that we prepared. And in the literature, we see comparable magnitudes in the freshwater and marine environments. So there's nothing specifically that jumps out when you initially look at this that, oh my goodness, survival in one environment is much higher or much lower than the other environment. So how do we look at this question within Puget Sound, within the Salish Sea, and what approach do we take to comparing and asking the relative importance of survival in freshwater and marine environments? So to do this, we propose to examine two questions and to apply these questions to populations across the Salish Sea as we'll outline here. So the first question is to partition things into total mortality, taking pretty basic, taking the eggs in the gravel and partition it into total mortality occurring in the freshwater and the marine environment. And the second is then to ask the question how variation in freshwater versus marine survival is contributing to adult returns. Again, taking this information about survival in the freshwater versus the marine environment and correlating it with adult returns. So we did this with two case examples where we had the data completely compiled to be able to examine the question, and then we go on to propose how we would apply this on a regional scale to other populations within the U.S. Salish Sea. So I'm going to talk about the case examples, and then Correigh will take over talking about what we are proposing as a 5-year plan looking forward. So our first case example comes from the Deschutes River, which is a population of coho salmon in South Sound. A couple thousand coho on a good year return to this river to spawn. And you can see that a majority of the mortality of eggs, total mortality, occurs in the fresh water. Look at this y-axis here. So a majority of the total mortality occurs in fresh water, and then a smaller percentage, 1 to 7%, occurs in the marine environment. But that over time that we had monitoring data for this population, that the proportion of total mortality that is occurring in the marine environment, these blue bars here, has been increasing beginning in about 1990, corresponding well with the results that we saw already this morning. If we look at the variation in marine survival, smolt to adult, and correlate that with adult abundance, we can see that marine survival indeed is well correlated with the number of adults that have returned to the coho salmon that have returned to the Deschutes River. It is not well correlated with freshwater survival, and that's a graph that's provided to you in the section that we wrote, but I am not including here. Now, this has been through good support that marine survival has been driving or contributing greatly to the declines in adult returns that have occurred for Deschutes River coho salmon. However, if we go to the Skagit River Chinook salmon, which is another well-studied population, Skagit River is Whidbey Basin, 6 stocks of Chinook salmon in the entire basin. The total mortality of Chinook salmon in freshwater is again very high, hovering around that 85% of total mortality, but lower than what we saw previously with the coho. And you can see that there is no trend over time. If we look at the variability, freshwater survival not correlated with adult returns, marine survival also not very well correlated with adult returns, again contrasting with the Deschutes River coho salmon. We have two different examples here with different types of results correlating or not correlating marine survival with the adult returns. I think Correigh's going to take it from here to talk about some of the other considerations that we might have.
So the Chinook example illustrated that in some cases marine survival might not fully explain patterns in adult returns. And I'm going to go over two examples or two considerations that highlight this issue, and then I'm going to focus on the research plan that we've come up with. What I'm showing here is the Skagit River upmigrants broken down into 3 life history types. Fry migrants, basically fish which migrate outside the pink salmon, par, essentially singular migrants, and your typical yearling smolt. And as you can see here, this is a fry migrant dominated system, and pretty much those fry migrants are determining the cohort size of the outmigration. Those fry migrants typically rear in the tidal delta, a large portion of them, as they're migrating through the system. So we can take this information and look at that fry contribution to better understand the dynamics in the Skagit River system. So basically now I've looked at the adult returns pre-fishing as a function of fry caught at the trap. And you see here strong evidence for density-dependent limitation that initially as fry go up, the number of adult returns go up, and it levels off pretty strongly. And so there seems to be a strong limitation based on that fry contribution. You can also look at marine survival as a function of fry as well, and that's shown in this graph here. And we can see quite the opposite effect, a strong negative function of marine survival as a function of the number of fry caught at the trap. And so this might support interpretations of size-dependent mortality or a match-mismatch hypothesis that these very small fish, when entering in to Puget Sound, are highly vulnerable. But the causes seem to be the density-dependent relationship in freshwater. So another consideration is spatial variation across Puget Sound. And so we've talked about this a little bit. Here are three examples within Puget Sound. So there's South Sound population represented, Hood Canal, and Whidbey Basin. If you look at South Sound, it kind of follows the story that other people have been telling about the big crash in Coho. But if you look at Whidbey Basin or Hood Canal populations, that doesn't it's not as typical as the story being told that they can do, that individual populations can do pretty well in the face of some of these larger scale phenomena. And so what this illustrates is that there needs to be a nested design that assesses spatial differences and assesses this freshwater marine component. So what we're proposing is basically a set of data needs that focus on these outmigrants and adult returns. And so there's a number of measurements we need to take to monitor fish in the system, but many of these are sort of, you can move them across systems. But two absolutely important ones to look at freshwater versus marine signals are outmigrant abundance and spawner abundance. And so what we propose to do is to put this, to build on the existing monitoring program that exists within the tribe and the state, to come up with a system of monitoring watersheds which capture the interbasin differences and enables us to look at a number of different populations and species. And so here's just an example showing what we can do for four of the major basins within Puget Sound: Whidbey Basin, South Sound, Hood Canal, and the Strait of Juan de Fuca. So there's a number of systems which are limited by the number of populations that can be monitored. So, for example, South Sound, there's only one pink Chinook and steelhead population that can be well monitored. But but there are places where we could improve monitoring efforts, so these numbers could be boosted here to get replication within basins and also get a better sense on a short-term research project, like 5 years, a sense of the spatial variation. And so with that, I'm happy to be done. Thanks.
Thanks to both of you. Next up is Dave Beauchamp, who will speak about size, selective mortality, regulating survival on the field.
Okay, excellent. So one of the hypotheses here is that size selective mortality is a ubiquitous process we see across a lot of salmon populations and marine fish in general. And in that, we're assuming that larger size at particular life stages confers a survival advantage on those populations to reach adulthood. Now, some of the critical things here are that this size that they achieve during a critical time may or may not result in mortality during that same period. It could actually be a delayed mortality effect where you're essentially setting these fish on a different trajectory where they have lower survival probability into the future. Okay, so within size selective mortality, we've seen there's different types of evidence that we can use to point to that, and I'll show you some examples from Strait of Georgia and Puget Sound here. In general, what we're trying to look at is that we can use this as a way to try and identify where there may be some processes that are occurring, help us identify what those critical periods of growth and sizes that need to be achieved by particular times, and relate that to overall survival to adulthood. And some of the ways we can look at that are either from correlations of size at particular life stages to overall survival, or also look at size distributions at particular life stages in the life of these fish associated with particular habitats and life stages, and try and sort through where where these shifts in size that are critical to survival may be occurring by virtue of truncation of, say, some element of the size distribution of those. Now, in order to do that, we need to account for the stock of origin of those fish and immigration or emigration types of dynamics, so that we're not misattributing loss of fish due to some other process than survival itself. Okay. One of the nice advantages of size selective mortality is that we don't necessarily have to rely on estimates of abundance through time. Kind of the typical way that we try and estimate mortality is what's the abundance at one point, and then what's the abundance at some later date, and look at what the proportional reduction would be. In this case, we can simply look at changes in the size distribution of the same cohorts as we track them through time. And so that gives us the opportunity to look at a larger variety of data sets in order to try and sort out what the signal might be. And then lastly, I think size selective mortality, although it may not account for all the mortality that we were concerned with, it provides a useful framework for trying to connect both the bottom-up and top-down approaches that may be affecting these populations through their lifespan here. Okay, so I'll give you a couple examples here. This is one from coded wire tag groups in Puget Sound over a number of years from 3 regions within Puget Sound. And primarily what I want to show is that we looked at the body mass of fish at various life stages of these coded wire tag groups, and then related that to smolt to adult survival from those same cohorts. And the size at release had very little correlation with that overall smolt to adult survival, whereas we had a very strong correlation between the size that these fish achieved by July and their smolt to adult survival. When we try to look at that same relationship in September, we still do have a strong correlation, but you'll note that the slope of the curve and the correlation itself is considerably weaker than what we saw in July. Now, one of the critical things to note here is that this weight in July is the product of these fish having moved offshore and growing on epipelagic food base for at least a month prior to their interception with the rig or midwater trawl. And during that time, they're increasing their body mass from 2- to 3-fold over what they expressed in these nearshore environments. So a lot of this weight that we're seeing is a product of growth during that offshore growth period. And lastly, the slope of this curve is such that you've got, for every increment in increased weight, we're seeing essentially a doubling in the survival rate there. So this can potentially have a lot of implications in terms of what factors are affecting growth and thus survival during some critical periods. It also may be useful as a forecasting tool to help us say, based on the weight of these fish during a particular time, are we going to have a high survival year or a low survival year from the resulting adult returns that come in? Another way we can look at this information is take a particular size or particular life stage of these fish from, say, seals or otoliths, and look at the size distribution of the juveniles that are sampled at large in the population. And if we look at some later life stage, this could be adults or some subsequent juvenile life stage. If those size distributions overlap, then there's no evidence of size selective mortality happening. But often what we see is a shift so that we truncate out a lot of these smaller size classes, and the survivors are considerably larger. And so if we can do that sequentially through the life stages of these fish, we can start identifying where there may be periods of size selective mortality, and also get a sense for the magnitude of that mortality rate as well. You might also note that in some cases we may see signals for alternative life stages of fish that may or may not be reflected in the adult returns, and so this is another way to try and identify which life stages or life history traits are actually contributing to adult returns at this under current conditions. And so we can do this by doing either scale back calculations or otoliths, and we've done this successfully for pink salmon up in the Gulf of Alaska, but we've also done a pilot in Puget Sound with Chinook, And so the idea, again, is like I say, you can count the circuli and then look at the distribution of sizes at particular circuli from juveniles that are caught from, say, this scale, and then revisit that with adults that come back from those same cohorts and compare those size distributions just as, like I indicated in that previous slide. And so this has been done. Here's a classic study from Keel River by Bruce Ward with steelhead, the size distribution of smolts versus the surviving adults. In all the years that they looked, you could see that there was size selective mortality that occurred between the freshwater smolt stage and the surviving adults that came back. And that was also reflected in terms of the size of the smolts, in terms of length versus their smolt to adult survival, with some extra or higher survival rates in El Nino type years. But more recently, that pattern's tended to fall apart, where now we're not seeing this relationship between smolt size and adult survival for that same group. And similarly, in terms of the number of returning adults per smolt, historically up through the 80s, we saw a nice strong correlation there where we're on a different trajectory in more recent times there. Similarly, this is some of Dick Beamish's work in the state of Georgia with juvenile Chinook. Again, looking at the size of juveniles that are captured in the state of Georgia at various points. If you look at the median size, those fish juveniles that contributed to the lower 50% of the juvenile population only contributed about 18% of the returning adults. And so again, you have some indication that you've got size selective mortality and a little bit of information in what life stage those things may occur. I've included this information from Chinook salmon in Puget Sound, but only for demonstration purposes, and the reason I'm doing that is because we can't track, they're going to be information from the same cohort all the way through, so I'm just using this as an example to tell us what we could do if we methodically collected this information. And what we have here is the size of these fish back calculated at different circuli numbers from fish that were sampled in nearshore habitats in July versus those that were sampled as returning adults from that same cohort. So this would be the first year of adult returns from that year. And then also, we didn't have juvenile samples from the offshore habitats for that particular year. We did have those for 2008 though, and we've plotted those on here just for demonstration purposes. What we're seeing, though, is that the nearshore fish are progressively deviating in terms of their size from the adults that successfully survived to return, whereas, again, different year, but the offshore fish that are in July are on a very similar growth trajectory to those successfully surviving adults. Okay, so some of the knowledge gaps that remain are we've only been able to opportunistically look at this sort of a question. And what we really need to do is do this in a much more methodical fashion where we're tracking the size distributions of fish through different life stages, relate the size of fish at particular life stages to their smolt to adult survival in order to play this out. And so if we can do this, we can start identifying, again, as Mara was mentioning, do we have these critical periods that may happen in freshwater, estuarine, nearshore marine or offshore marine, or even beyond life in the Salish Sea, so that we can start identifying where we have some options to work on what may be affecting those survival rates and growth, or where we may just have to account for those instead. Just as an example here, we have different life stages where you have the opportunity to monitor these fish. So when the fish first either come out of hatcheries or in some cases may have some very intensive wild population monitoring, we know how many fish are leaving the hatchery. We know what the size distribution is at release. We can potentially take scales to start the process of looking at what their initial size was, and we know the timing of that release as well. And as we track them through different phases of their life, we can start doing these examples of, say, looking at what their size is at release versus their marine survival rate, and certainly look at the size distributions of those fish both at the juvenile life stage as well as some subsequent life stage there. For smoke traps, again, we have the opportunity to look at abundance, size distributions, again, collect scales and do the timing. In estuarine areas, we can't necessarily look at abundance, but we can look at density as a surrogate for that. Again, size distribution, scales, and timing. And then as we move offshore, we can collect that same suite of data. There is some, if you impose a certain amount of effort, you can actually get abundance estimates. Again, Beamish has published a paper on coho. If you're willing to put in the effort, you can get yet another estimate of abundance for particular species there. And then, of course, with adult returns, we can get the abundance estimate. Again, Mara warned us that we need to make sure we're paying attention to whether this is adult run size, just simply catch, or adult plus escapement, so we've got a completely reconstructed run size there. But again, we have the opportunity to look at size distribution, the scales, so we can do those back calculations, and the age distribution, as Kurt was mentioning earlier on, about how things may change through time. And if we do that, then we can start doing these sorts of comparisons where, again, I showed there was some signal where steelhead showed a strong relationship, at least during certain decades, between their marine survival and their size. Whereas with some of these other species, we may have to do some other things. Where I showed examples in the coded wire tag data for hatchery Chinook, again, where you've got a strong size selective mortality that is tied to early marine growth. In the Skagit system, though, there may actually have something that's tied more to nearshore rearing. We don't necessarily know that, but again, there's evidence of that. And so this is just sort of a schematic of how we might be able to play this out into the future. And with that, I'm over time, so I'll quit.
All right, next up is Josh Chamberlin, who will speak about the hypothesis that out-migration timing and residency influences the magnitude effect of competition, predation, and environmental variation on survival in the state of sea. And I should say the presentation is titled in order on page 7 of your agenda packet. Thanks, Josh.
Thanks, Laura. So, as Laura said, I'm going to talk very briefly about two separate hypotheses. The first of which is out-migration, the idea of out-migration timing. And we're basically asking the question, and it's a question that's asking about a number of interrelated things and a number of interrelated conditions. And the basic question we're asking is, do shifts in the timing of out-migration increase or change to the magnitude effect of several environmental conditions on the overall survival of salmon in the British Sea? And these environmental conditions could be a number of things, and I think the best way to sort of conceptualize this is using the mismatch hypothesis that was brought up earlier, as developed by Cushing in 78. And it's basically the idea that you have So the basic idea is that you have some sort of environmental variation that's varying through time, and depending on your trait of interest, in this case out-migration timing, you either have a match or a mismatch based on the overlap of that timing. And neither one is better than the other, and it wholly depends on the environmental variation you're either matching or mismatching. Say, prey availability, with a peak in prey availability, you would like to have a match. Whereas if it was peak predator abundance or peak competitor abundance or something like peak blooms with some harmful algae, then you would likely want a mismatch. And there are several reasons why, or there are several reasons why there are differences in out-migration timing. One of which is species. We know that chum and pink typically migrate earlier than, say, coho and chinook, and have a less protracted, less broad distribution of out-migration timing. There's also, within species, this figure from Beamer and Larson, and alluding to what Correigh had mentioned earlier about life history tests, you can see for this being chinook and Skagit, but there's significant difference between like history types where your fry migrants are migrating out much earlier than your other three life history types, which were in the delta for some period of time. And this would also be the case where you bring up, the differences between ocean type, stream type, or suburban yearling, depending on where you're from. There also may be reasons for these shifts at a more local, regional watershed scale. And this is unpublished data from Meteorological Fresh showing mean catches of Chinook in the Hamish estuary. And you can see here, you can ignore the magnitude there, but if you look on the x-axis, you can see that in 2002 and 2007, your outmigration time appears to, most of the outmigration was after June, whereas in 2005 and 2003, most of it, if not all of it, was before July. And what we know about these 2 years here is that they are abnormally warm years with relatively little rainfall. And what that seems to have done is cause the temperatures in the estuary to reach their threshold levels earlier, forcing fish to move out sooner, which could have deleterious effects based on size, selective, mortality, and other mismatch timing issues. So as far as how we can track this, of course, smolt traps are the best way to go about this, and there's several of those being used throughout the region, monitored by WDFW and tribes. We need to obviously continue to do that, make sure that we're getting reliable efficiency estimates. I would also urge some more intensive estuarine studies like those that are currently going on in Skagit and Ocean this fall, as Correigh pointed out, to kind of compartmentalize where this mortality is occurring, as well as I would argue to expand some more of the life history diversity qualities of Chinook throughout the region. And then, of course, this is interrelated to a number of different hypotheses, and I'm just talking about the differences in outmigration timing, the differences in the environmental timing and the environmental condition will be addressed in later hypotheses. Switching gears dramatically, as many of you know, here in the Salish Sea, in addition to the typical ocean migrants, we have a considerable number of fish that seem to reside for some period of time, if not all of their adult life, before returning to the rivers that spawn within the Salish Sea. We really have relatively little information on what that does to affect survival. And more importantly, how does the duration of their residency in the Salish Sea affect survival? This is primarily Chinook and Coho, but to some extent, Beauchamp as well. Now, the figure on the left is some acoustic telemetry work we did a few years ago in Hood Canal on the hatcheries of fish that were intended to recruit to the resident. And you can see that survival definitely decreases over time. However, it was relatively high even at the end, although this is a very short period of time. This is the first roughly 100 days in the marine environment. So as far as the very early pictures of marine survival, we can see that it decreases, but this does really nothing to tell us what's going on later on. We also know that from O'Neill and West in 2009, there appears to be some elevated levels of contaminants in the tissues of residents. I'm going to let Sandy talk about this a little bit later. She's going to address that, her hypothesis. But there's other things that we're not really sure about. One being the effect of predation on these fish. There's relatively large population of marine mammals in the area. How do they interact with these fish, these resident fish? And as well, there's the question of competition. And we've talked, many people have mentioned the prey availability question, and how does that play into the resident question as well, as long as the competition with other collaborators. The bottom line is with the resident fish is we really know very little. And I think the first step in going forward with this is to identify a way to identify these fish, which for right now is basically based on location and timing of catch. And I propose that we try to develop some sort of odorless microstructure, microchemistry work to be able to identify these these individuals on, say, the spawning ground based on the overlooked microstructure. This, of course, is predicated on being able to find some difference in the water chemistry between Salish and Pacific Ocean, but I believe it would be a worthwhile cost. You can also couple that with some stable isotope analysis. I have a tooth telemetry on here. In my opinion, it's probably the priciest option, especially in the face of the waning infrastructure here in Puget Sound. I also think that the behavior of these fish makes it a difficult tool to use to assess survival of the residents in the fish. And I'm way over time.
Thank you, John. All right. Next up, Ken Warheit will talk about diversity among salmoniid populations, conferring temporal stability and long-term persistence of the species within the COC, which is the portfolio effect.
Thank you, Ken. I have 5 minutes, so I hope not to go over, but and this thing, right? So this is essentially the hypothesis, I think we just read, diversity among salmoniid populations, compare temporal stability and long-term persistence of species. Portfolio effect is part of this. I'm going to talk mostly about diversity, and I'm going to try not to keep doing that. So, move on. So, this is it, and from a theoretical standpoint, biological systems are hierarchical. And another way of saying that is temporal stability and persistence at one level in the hierarchy, so take any one of these levels here, is a function of processes that occur at that level and perhaps processes below that level, both in terms of diversity here. In the written part of this document, I provided several examples. I started off with an example about a molecular example using MHC, how diversity at an individual can confer could result in more stability for that individual, higher survival, and perhaps also greater longevity for that population. Christy Miller-Saunders can talk more authoritatively about that. But I also gave examples from the population and species level with terrestrial animals, and then I also gave examples from sockeye work in Bristol Bay about how diversity here at a lower level can confer stability at a higher level. A corollary of this, now we won't be able to test things like the portfolio effect in Puget Sound, for example, and I gave reasons in the document itself. But a corollary of this is that factors that reduce diversity at any level puts the long-term stability at the higher level of systems at risk. So if you reduce stability at the population level, you can reduce, you can put at risk the stability of for example, a metapopulation of species at the higher level. I'm going to talk about unpublished work that WDFW has using Chinook salmon and Puget Sound as an example. And the factor here that I'm going to talk about is hatcheries. So these data come from, these are all the sampling locations that we have for this. I think there's, 20 some odd sampling locations. Focus on the yellow with the little black squares in the middle. These are late run, so this is adult run finding. No kidding, 3 minutes. These are late run Chinook populations that are derived from a single hatchery, Seuss Creek. There's natural spawning occurring in these areas as well, but a lot of these populations are dominated by that Seuss Creek hatchery. And then also look at the blue right here. These are early run populations, generally from North Puget Sound, as you see, and they're mostly wild populations, and also concentrated. The Skagit River populations are focused in this square right here. That thing is really annoying. So what I'm looking at is pairwise geographic distance versus the pairwise genetic distance. And focus on the black line here. These are for those yellow collection areas, which are late run, derived from hatchery stocks. They basically have there's no relationship between pairwise genetic distance, between pairwise geographic distance and pairwise genetic distance. But if you look at the early run, remember these are the North Puget Sound, not dominated by a hatchery system, you do have a good relationship. Also, in any given area, you find that there's greater genetic distance among the populations with the blue early run than there is with the late run hatchery dominated systems here. Another way of looking at this, as I looked at two populations that square with the Puget Sound with the Skagit River population, there's only 10 samples, 10 populations in that group. The maximum geographic distance in that area was 76 kilometers. I compared that with all of the late run Greene River, Goose Creek, hatchery dominated systems. There was 45 in 45 pairwise combinations. The maximum geographic distance there is 292. You can see that there's a significant difference in the pairwise geographic distance, that these guys right here are devoid of genetic diversity, essentially compared to these guys, a lot more genetic diversity, even though these guys are coming, genetic differentiation, even though these guys are coming from one geographic area. So observation 1 is being obliterated by the reporter here. The late run population is dominated by a single hatchery population, but now widespread throughout Puget Sound have reduced genetic differentiation at this point. Okay, so this is now looking at, obviously, year by proportion of the run, total run, that is, so I'm looking at the proportion of the total run divided between early, the total run, this is going to be pre-freshwater fishing. So this is going into the rivers, total number of fish coming into the rivers, how it's divided between early run populations here in North Puget Sound, not dominated by hatcheries, and late run dominated by the hatcheries. And this is the actual total run. You can focus on the early part right here, and then the last part right here. Roughly, the total run size is the same, but you can see that the run at one point was half early run and half late run is now completely dominated by the late run dominated by hatchery systems. So then you have observation 2, roughly 90% of the total run for Puget Sound Chinook is now from the late run population dominated by hatchery production. Put these two together. Conclusions. Past. In the past, we had a balanced mix of north and south populations with varying run timing. Now we have a system that is dominated by late-run hatchery origin individuals from a single ancestral lineage. That would be the Greene River lineage. So from a population standpoint, looking at that hierarchical level, reduction in genetic differentiation, the system is now more homogeneous. And I have one more slide here. So these aren't all the remaining questions. These were the remaining questions in my head at 10 p.m. last night. So the first one is unanswered at this point. It has the hatchery-driven reduction in population differentiation. Has that limited the recovery of the Chinook metapopulation in Puget Sound? Secondly, has it also limited the ecological and evolutionary potential of that Chinook metapopulation? And then what about coho and steelhead? There's been a considerable amount of work done on coho that has shown that there has, as a result of hatchery practices, there has been a reduction in genetic differentiation. We are currently working on that question with steelhead. Now, I do want to add that there is no direct research program that I'm suggesting here. What I am suggesting is there's a lot of information, all the stuff that we've talked about right here, and what you'll hear about later on today and tomorrow has diversity as part of its issue, as part of a factor related to it. And I am suggesting that there are genetic components that can be added to this question. Particularly, I know Christy's going to be talking about fish health and genomics with that, but we can add it in terms of population and metapopulation stability as well. Did I do it in time?
Thank you, Ken. Michael will tell us about developing an intensive monitoring program in general research.
So I'm going to be really quick. Just refer to page 36 and 37 of the Puget Sound document that we released. What we tried to do here was just roll everything together, or at least a lot of the components together across the different hypotheses and research recommendations that were discussed. And it's just the graphic portrays what an intensive monitoring program might look like. And then there were some research recommendations on the following page. I'm not going to read them right now, but go ahead and read them for yourself, and we can talk about them in a little bit. Okay, thank you.
Okay, thanks, Michael. And everybody should have gotten that when you checked in that packet. All right. So next up, Erin Rechisky will talk about using marine telemetry to define when their mortality of Salish sea salmon occurs. All right. Thank you.
That's a question that everybody wants to know: when and where does mortality actually occur? And I just quickly want to say that before I started working with David Welch at Kintama Research, I was a graduate student of Carl Walter here. And when I first got to UBC, people said, Carl hasn't had a female graduate student in years. He makes the girls cry. And I said, he's not going to make this girl cry. And he didn't.
So his bark is worse than his bite, but maybe it's because I'm from New York and I have thick skin. Right, exactly. So first I'm just going to give you an overview of the post array, kind of tell you where it is right now. Then I'm going to talk about a case study. I'm going to present some results from Chilko Lake sockeye. And if I say Cultus Lake, I mean Chilko. We did a 4-year Cultus study a few years ago. I'm talking about Chilko today. So the Chilko Lake sockeye study was funded by the Pacific Salmon Foundation, and we worked with Scott Hinch's lab on that study. About 10 years ago or so, David Welch said, hey, we can actually measure early marine survival in the Salish Sea of salmon smolts if we can do two simple things. One thing is, can we implant, or if we can implant, transmitters into salmon smolts without killing them? And the second thing was, can we deploy stationary autonomous acoustic receivers near the bottom of the ocean, keep them in place, make them trawler-proof, and then recover them so that we can recover the data. So two very simple things. But we've actually been doing this since 2004 and quite successfully. So the transmitters over the past decade that are manufactured by Vemco have gotten quite a bit smaller. So they were about 3.1 grams. You can't see the V5, but the V9 tag weighed about 3.1 grams. So you can only put these into larger salmon smolts. But the V5 tag, which is the latest tag, has just become commercially available. It weighs, and you can't see, only a half a gram. And so it's considerably smaller, just a little bit wider than a pit tag. So these can be used in smolts that are 95 to 100 millimeters in torque length. And I can tell you research, we've implanted transmitters into over 12,000 smolts using all these different tag sizes. And we've also implanted another 1,000, 1,500 fish with these transmitters to look at, and held them to look at tag retention and survival in captivity. So in the early days, the array was deployed, the individual acoustic receivers, that's the black cylinder right here, they were deployed as this buoy, and all of these buoys were deployed in the Salish Sea area beginning in 2004. And they were all connected by ground line, lots and lots of ground line. And this was a really good way to get these buoys back. So we had an acoustic release, you pop them up to the surface, and then the long line is just, we use commercial fishing boats, as you can see here, and the long line is just put on the drum, and you collect it just like you would a long line gear. It worked really, really well until the trawlers got to them. And sometimes we had something like this that came up. Now this wasn't typical. This was probably one to see that, which was a little bit of a problem early on. Sometimes the line just cut, other times we had this big one. But Vemco developed a different type of a receiver that had an acoustic modem, which was great, because what we could do was deploy these receivers individually without the ground line, and the yellow float collar that you see there around the VR3 or VR4 Vemco receiver is a custom-made buoy that David designed to be trawler-proof, and it's been quite successful. So this boat here is loaded with the full gamut of the different designs that have been used over the years. So we've got the older float collars, the newer float collars, the pop-up, the two different pop-up designs, different anchoring systems. So this has been refined over the years. So the extent of the post array has ranged from Alaska down to California. And some of these lines, this is in the current map, some of these lines are currently in, some of them are not. But what we want to focus on here is really the Salish Sea area. So these three lines, this is the Queen Charlotte Strait acoustic subarray. This is what we call Northern State of Georgia subarray, and the Wandasuka subarray. These are still in place, and these are all, or were all, managed by POST, for the Pacific Ocean Shelf Tracking Array, but a private. So what's happened recently is, and this is just recent over the past couple of weeks, the Ocean Tracking Network, or OTN, they have subsumed the management or the responsibility of those three subarrays in the Salish Sea area. So OTN in the future will be managing the arrays, and Kintama actually does the maintenance of the arrays. And we also, Kintama also has a series of subarrays in the Fraser River. So I'm going to present some Chilko Lake sockeye survival results. Over the past 2 years, this should say 200 by the way, not NA. Over the past 3 years, Scott Hinch's lab has tagged over 1,400 salmon smolts from Chilko Lake, and using two different transmitter sizes, the V7 tag and the V6 tag. And before I show you the survival results, I want to show you an animation of their movement so you have an idea of where these fish migrate. Should work. Okay, this animation shows 3 different release curves. So you can see here that most of the fish migrate take the northern route going through the northern Strait of Georgia and through Johnson Strait, and they're detected off of the Queen Charlotte Strait subarray. But you can see that 3 fish, and this is just 2011, 3 fish were detected on the Wanda Fuca array, and 2 of those 3 fish survived up to what we Lippy Point, this subarray that's off the northwest coast of Vancouver Island. Oops, I didn't mean to show that again. I would, but I don't have time. This figure here shows the cumulative survival from release at Chilko Lake. And so I've got 3 different release groups plotted here. This is 2011 data. And as you can see, the 3 different treatment types have very similar survival in those different habitats. Now, one thing you notice right away is there's a pretty steep decline in survival immediately after release. Now, Chilko River is nice and clear, and the smolts, I guess, presumably were getting picked off pretty quickly, and as a result, the fish migrate primarily at night, which is interesting. And then there's also mortality that occurs in the Chilko River. And we're able to partition the survival in all these different rivers because there's acoustic receivers as the fish migrate down the river. Now, what's really interesting is that in the very turbid Fraser River, the mortality or the survival of these fish is near 100% over 400 kilometers. And so that was pretty remarkable. We've got a pretty good survival estimate here to demonstrate that. In the Strait of Georgia, once the fish enter the ocean, the survival declines, and again, further declines through the Johnstone Strait area discovery passage up to Queen Charlotte Strait. By using acoustic telemetry, we're able to break the migration into all these different segments, and we can identify where our mortality is occurring. And the survival all the way from release to Queen Charlotte Strait, a distance of over 1,000 kilometers, was approximately 10%. Now, 90% mortality sounds really severe, worrisome, but the return rate of Chilko Lake sockeye, since people in the audience are definitely more of an expert than me on this, is only a few percent in recent years. So 10% survived to Queen Charlotte Strait, but there's still another 70 to 80% mortality that's going to occur out in the coastal ocean after this time that we track them until adult returns. So of course we can also get some really interesting behavioral information using all this telemetry data. And what we have plotted here, the gray bars, these are the migration rates. So in the river, migration rates, they vary, but they're quite fast, as you would imagine. And once they hit the Strait of Georgia, migration rates slow way down because they're not under the influence of the river anymore. Now, when they migrate through the Discovery Passage in Johnstone Strait in that area up north, the migration rate increases a little bit. And the total distance traveled for these small smolts is, the total distance traveled is over 1,000 kilometers, which takes about 45 days, so about 6 weeks. So we're able to track these fish during the first 6 weeks of their life. And actually, there's an array in Alaska as well. So with higher sample sizes beyond this point, then we would be able to track survival up to Alaska as well. There's another, I'm not quite sure, 500 kilometers north of southeast Alaska line. So I used the Chilko Lake sockeye study to demonstrate how effective using marine telemetry arrays can be. But I also want to emphasize that the array has been used for the other species of Pacific salmon, so steelhead and coho and Chinook salmon. And I just put up a couple or half a dozen studies that were published just to demonstrate this. And I also put a few at the bottom of my poster here in a really tiny font in case anybody wanted to see. But so these studies that I showed here, most of them They do have, let's see, there's coho, this one here is steelhead, there's Chinook studies. Now, these studies are beginning to scratch the surface. In many of these studies, sample size just is large enough where the survival has been estimated in a more confined area, but with larger sample sizes and an even more dense array in the Salish area, it is entirely feasible to estimate survival of some of the species that are of interest today. So yeah, that's it. Thank you.
Thanks, Erin. That's great. Yeah. Okay. Thank you very much. And now rescue reading. We'll talk about juvenile salmon studies being given. I'm sorry, enlisted. I'm really excited to be back.
Yes.
So, Dick and I were talking about what we were going to talk about in our 2 10-minute segments here. I don't know how many we have left, and we got into quite a good discussion about it, so we decided that we would do that here, that we would sort of have this two-way discussion, and hopefully that will stimulate some discussion in the audience afterwards. And before I start, I'd like to extend our thanks to Brian and Michael for organizing and collecting this August group of people all interested in the same issues. I don't know which button I press in. Okay. All right, so the first thing I did was just put together here a very general idea of what we're looking at, just breaking it out into the phases, freshwater phase that Erin just discussed so well with us, moving into the early marine rearing phase, just Greater Georgia and Puget Sound, and then out into the open ocean phase. And then and we believe, from our research in the past 20 years, that under the current conditions, it is the early marine mortality that determines the year cluster and adult return abundances.
And what we were talking about, what we were talking about is that particularly for coho, in the 60s and 70s in Alaska, where you're getting 14 or 15% survival, then the freshwater mortality or survival was probably equally important. But as Rusty said, it's been in the recent years when you're getting down to 1 or 2%. That's what we're seeing in the marine phase.
Okay, so I think that's good one here. No? Okay, so what causes this early mortality what causes mortality in this early marine phase? We've heard a little bit about predation, we'll hear a little bit about disease. Starvation, I've got in brackets there because they don't have to starve to death. They can be short on food or energy and have an impact on mortality. And then the physical environmental parameters, which we've heard a great deal about this morning, and competition, direct and indirect.
And then another thing that we were talking about is that even though fish can leave, let's say leave the Strait of Georgia go through Johnson Strait, they're basically swimming games. They're already predetermined not to be able to survive the winter. So the fact that they actually migrate to some place doesn't mean that they're going to survive. They may have lipid problems or other problems. Just because they're swimming doesn't mean they're going to survive the ocean winter.
Okay, so this is just broken down a little bit further here, turning in those things we just discussed about diet and predation of size and the various interconnections between the two. And I put climate over top all of them, and in this case we're defining climate as the physical environment, whether it's the local estuary flow rates, regional things like salinities and temperatures, or at the basin scale as we were hearing this morning, LP and PDO and all the other O's. Okay, so what affects early marine mortality? The first thing we're going to focus on here is, as we've already heard a couple of people talk about here, is size. And you can break that out into size per se, and increased size leads to increased survival, presumably through various mechanisms such as increased predator avoidance, increase in prey, types of prey that you can go after, whether it's size or chasing them in terms of swimming speed. But there's also growth rate. And in this case, we have this idea that the faster growing fish survive more, which comes back to ideas that Dave Beauchamp was talking about a little earlier in this presentation. So, again, just to outline a few things here. Coho and Chinook both enter the marine system generally at considerably greater sizes than pink chum or sockeye, although, of course, you will have fry migrants of Chinook, which will be small like that. Hatchery coho at time of release do generally tend to be significantly larger than the wild migrating smolt. And in our work, we find that even in September, when we're looking at clipped hatchery fish, they're still significantly larger than the non-clipped wild fish that we're catching. We can do some correlations that we've talked about here, and again, kind of in agreement with some earlier speakers, we do see positive correlations with fork length, with marine survival, with our abundance estimates, and with CPUE, both in Strait of Georgia and Puget Sound. In the summer data, it tends to fall apart. The relationships do tend to be a bit weaker in the September surveys.
So what we spent some time talking about, again, speculation, is that a fish that achieves its maximum possible growth rate, so the temperature is optimal and the food availability is optimal, so there's very little energy spent searching for food. That optimal feeding rate gives you the optimal survival rate. And then everything that detracts from that, higher temperatures, reduced availability, directly but probably inversely affects survival rate. So there is a maximum possible survival rate. So let's hypothetically say it's 14 or 15% for coho. Some of you may remember many years ago Don Alderdice and Hilton and someone else, shooting maybe, right? Published a paper and they proposed that coho released from the hatchery in the state of Georgia, the optimal survival could be 40 or 50%. Right? So that's the calculation. And again, I'd like to cite that because it's an indication of what someone thought the maximal survival could be in absolutely optimal conditions. So when you get 1 or 2% survival, we're looking at a substantial amount of energy that's taken away from growth, and that we think represents the decline of survival.
Okay, so then just to sort of continue on with this, again, sort of similar to what Dave mentioned earlier, we get a very strong correlation with fork length and hatchery survival. We see here in this is the clipped fish, which I should mention, in the Strait of Georgia in 1998, when they shut down the fishery inside in the Strait of Georgia for coho, we also initiated a mass marking program for Chinook. So we get a substantial number for coho. So a large number of our catch we know are hatchery coho. So it's easy enough to pick them out, and we see a very strong relationship with size and survival, which in this case is stronger for the hatchery fish. And this was something that I sort of was talking with Mark Trudell about as well, and he's going to talk a bit about this again tomorrow. And this is the growth rate. This is the growth between the summer surveys and the fall surveys. So just sort of taking the mid-date of the summer survey and the mid-date of the fall survey, taking our average size and divided it out into growth per day. And it kind of surprised me to see this really fairly consistent, approximately 1 millimeter per day in the Strait of Georgia, with a few years that we had some obviously issues. And then a bit of more diversity here in what we see in Puget Sound. But I think there's a couple of reasons for this. Dick mentioned earlier, one of the things we found in our earlier years of doing this work, when we were doing more work out on the West Coast, that the coho leave Puget Sound even in July. If we catch 100 CWTs out on the West Coast in our July surveys, 85 of them would be from Puget Sound, and 14 of them would be from Columbia River, and 1 of them would be from the Strait of Georgia stocks. So the Puget Sound coho are clearly leaving well before the Strait of Georgia coho. And even in September, we rarely get Strait of Georgia coho CWTs out on the West Coast. They tend to be more into October. So the larger fish reaching a certain size or a certain growth rate are clearly leaving, and it appears that they reach that size or that potential earlier in Puget Sound than they do in the Strait of Georgia. So something that I don't think anybody's talked about yet is diet. As that feeds back into growth and size, and you have a number of issues here. We have quantity versus quality. We have seasonal changes in the diet, so I'll go through a bit of those. And the question is whether those are directed or those choices by coho in September to switch diets, or is it because their food source from the summer months has now moved on to a different stage or is in some way not available. And then you have your general climate variability or weather, as we might call it, versus sort of these long-term trends we're seeing in global warming laid over that. So this is a juvenile coho salmon for Strait of Georgia, hatchery reared. So these would be clipped, and these would be primarily unclipped, primarily wild, but there would be a small percentage of hatchery fish in here that are not clipped. So it's not quite wild fish. But you can see generally it's pretty similar. You have amphipods in the blue, decapods in the red, euphausids in the yellow there. There's another category in the white here, which is just anything else from polychaetes to seaweed to plastic hooks, anything else we find in there. And the black are fish. And you can see for coho, even in July, that fish comprise a significant proportion of the diet. And this is in September, and you can see quite a bit of change. Same colors. Amphipods are now much more important in the diet. Decapods have dropped out. The euphausids, again, much more important, and fish continue to be important in some years. 2006 here is very important. So the question is this a choice by the animal to switch to something like euphausids and amphipods, which are perhaps more energy rich at this point? One of the theories we have is, well, why don't you talk about that, Dick, the size versus energy?
Well, there's two things here. First of all, would you want to only have 5 minutes?
Yep. While he's talking, I'm just going to show you the same thing for Chinook.
So I'm going to just briefly mention that our Pacific Advantage Fish Commission is putting together a book on the essentially the ocean ecology of salmon. And Larry Whitecamp and myself and a few other people, Leon Shaw and Vladimir Rechisky, are doing a chapter on coho, which we have the draft done. But I'm mentioning that because it's amazing when you look at the diet of the juvenile coho, this age group, how similar it is all around the Pacific. And I would not have expected that. And later on, they eat some different things, including different species of fish. It's amazing how similar it is. So what was that?
The seasonal shift in diet, the question is, do they shift in diet because these animals are no longer available, or are they shifting in diet because they're preparing? In the summertime, the paradigm is to grow. You want to get bigger and longer and swim faster and escape. By the time you get to September and October, you've changed your priorities. Now you're putting on energy for the winter. So are they switching to energy-rich source of food for putting on energy, or are they switching because that's what's available? And the decapods and things that were there earlier in the summer are now in a different stage or moved on.
We sometimes disagree with you, but it's lots of fun. But we think that maybe I shouldn't say we. I think that the determination is made earlier, and that what they eat in September is what's available. And by September, their ability to survive may already be predetermined. So many of those fish are swimming dead fish.
So this slide here is just putting all four together. You have coho here in July in Puget Sound and Strait of Georgia, in September in Puget Sound, Strait of Georgia, Chinook in Puget Sound, Strait of Georgia, July, heading up to Puget Sound, Strait of Georgia in September. And you can see that they're very similar between each other, between the two regions in the various surveys, and that there's more variability between seasons than there is between the regions. And then just for fun, I thought I'd put this in this morning with chum.
You can see they're very, very different, and pinks would be more like chum. So coral and chinook, very different diet, very similar diets, very similar survival trends, similar, whenever forcing these reductions in marine survival seem to be acting on chinook and coral similarly, and then pink and chum, which have completely different diets, different sizes, they seem to be doing quite well.
Similar mortality between, maybe not quite, but between Puget Sound, Australia, and Georgia, but why do Puget Sound coral need 2 months before the
Yeah. And in terms of looking at marine survival, anthropods are quite strong, and fish in the fall only for chinook. So even with all this diet stuff, we're not really seeing anything with a diet that's strongly related to marine survival. And then the last thing we're going to quickly talk about here is competition. We have competition with hatchery and wild salmon, which doesn't seem to be any differences in diet, but certainly in terms of survival, we're seeing that. Competition between salmon species, and we've heard a couple of speakers already today talk about the potential impact of pink salmon, the large numbers of juvenile pink salmon competing in the odd years, and then competition with other species, either directly with competition for space or food resources, or indirectly feeding early in the year. Okay, so some of the things we talked about, what we think needs to be done. Go ahead, Dick. Okay, I'll do it. First one, conduct systematic long-term plankton monitoring throughout the basin, beginning in late February, just prior to the onset of the spring bloom, and continuing to at least the end of September. It'd be nice to be able to do that every week for that period of time. Secondly, conduct research on the very early first 4 to 6 weeks of marine mortality of salmon timing, of the juvenile salmon timing species dependent, of course. And I should say both of those were also recommendations on the recent Cohen Commission. Whoops. Sorry, that's going the wrong way here. 3, we need to improve our knowledge gap of major causes of ocean mortality of juvenile salmon, as we just heard a couple of talks about. And then lastly, sort of the new thing on the block in the last couple of years is the DNA technology. We're really collecting a lot of DNA samples now from our fish. And once the cost of this comes down a bit more, I think that's going to be a really valuable tool, and it's going to allow us to take all of this work that we talk about and bring that down to the stock level. And that is going to certainly increase the complexity of the issue, but I think it might clarify some of the muddiness that we see in doing these various correlations and such. Okay. Now everybody talk.
Thanks very much, both of you. Okay, so now it's time, that's what's going to work, for our first discussion session. And just quickly a reminder, please use your name tags of Alan and Ellen for you. I will try to hold the last 10 minutes of the conversation for observer comments and questions. And so, the questions are up here on the screen, but we'd like to refer to. So, launching in. Is there anything that we missed under this heading of the silvertone method? Okay. Alan was first, and then Brian, and Tucker. Okay. Go ahead, Alan.
I would suggest that something that was missed earlier was there was no reference to the NOAA. And we have been collecting photograph data since '94 with collecting Chinook tissues since 2005, and we could distinguish all of the hatchery-released fish from natural fish. And I would like to see that included back in the area studied, because it is one of the major population groups required for survival.
Thanks, Alan. Okay, Brian.
Can I just address that for a second? In our surveys, we in the last couple of years, we've just started doing a little bit of work in on the inlet, but really the tidal flow in there, as we heard earlier, is just really wicked, and we're really limited on where we can fish once we get out of trade and Georgia or Puget Sound.
Okay. Potentially the head in a second there as well. Brian?
Yeah. So this is a discussion of the Salish species. In the marine phase, the effort also partially focused on fish in the Salish Sea, but all fish go out to the ocean. So one of the major axes of variability, well, not all the fish, many of the fish, but one of the major axes of variability is when they go out to sea, what the conditions when they go out to sea, where they go out to sea. So that's what the animal is a lot about.
the timing of when the fish left. Great, thanks. Arthur, that's next.
Hi, thanks. I have it's more of a background question. I think of the Salish Sea as being geographically or oceanographically sort of unusual in that it's a huge estuary system, but it, in terms of water properties, it's kind of like the ocean. And I wonder, from the salmon point of view, like, what would it be like to be salmon if the Salish Sea didn't exist? You know, if it was just like the Columbia River coming out, very short, intense estuaries, goes river to ocean. Like, what, the fact that there's this giant Salish Sea fin there that's not really ocean and not really estuary, is it a benefit for them, or is it just an annoyance?
Think of it as a giant river queen.
So I just had a word of caution on using acoustic tags to estimate survival because you make a lot of assumptions, and one of those is whether it affects the behavior of predators. We've had a study on the Columbia River looking at tagging adults with acoustic tags and dummy tags and tip tags, and there's a huge tag effect. So we've looked at now the behavior of seals and sea lions when you put a tag in their tank. They can hear them, and in fact there's some work being done right now at Santa Cruz with these seals and sea lions that are trained to behave in response to noises. They've estimated that harbor seals can hear those tags perhaps as far as 2 kilometers away. And when they learn that those are dinner bells, the whole assumption about affecting the behavior of the predators is not valid anymore. So just a word of caution on what assumptions you're doing.
Okay. Are you going to respond to that?
Yeah, I think Jeffrey's, I'm working on some of this acoustic tagging work. We actually put Demco tags on sea lions, and there is evidence. I don't think the evidence existed before that seals and sea lions could hear these tags, but we knew all along, or we should have known all along, that harbor porpoise and Gulf porpoise, the dolphins can hear them. But we knew that already. So they're already predators on smolts, and the dinner bell effect is, what Michelle is finding in the Columbia River is pretty remarkable about how these pinnipeds can potentially target acoustically tagged fish. So I think it's a really big issue.
Yes, for layperson, that doesn't sound good. Okay. Do you have a question? Should be good. The right question is.
So this is a new issue. This is something that came up a decade ago.
Right. Close to. Yeah.
Not a rock star. So, and I've seen some of this. I've actually seen some of this recently, and I've made myself about this tag effect on the adults. I'm curious though, is there any evidence that just because a marine mammal can hear a tag, can it pinpoint and hone in on individuals? So we're going to do some experiments, and in fact they
we can just talk to them.
So they tag, they are targeting the individuals. Some of Michelle's tags actually had temperature sensors on them, so she could tell when they got eaten by the marine mammals. The temperature went up, so that tag wasn't just broadcasting a number, it was also broadcasting a temperature. You could tell exactly when they got eaten, and she was actually able to feel all of the sea lions or seals, whichever they were, around based on the live tags. We're going to do some experiments this spring where we'll have cameras or a Dixon with a tag in front of it and see who it is that's coming in. The question is it in the Columbia, we visit the sea lions or the seals that are doing those predations.
This is up at below Bonneville?
Throughout the lower estuary, she has very little triangle depth, which is actually quite a ways below Bonneville, where a huge number of her tags are disappearing. So, yeah.
Another comment on that, we've been working with John Payne and put Benco business card tags on 8 sea lions at Bonneville Dam and the Columbia River. And we got the Benco tags back from 4 animals, to dump the data from, and those 4 animals that had business card tags on had interactions with about 100 different acoustically tagged animals in the ocean, out of the Columbia River. And, John's comment was that's probably not just coincidental contact with those animals. That the few tags that are out there, the fact that 4 sea lions encountered 60 acoustically tagged animals, suggests that they actually can hear them and find them in the ocean.
Great, probably my time fish. All right. So it sounds like we need to add the dinner bell hypothesis to our list. I have Ed next, then Bill, then Dave, and then Christopher. Am I missing anyone with their hands up? And Art. So, Ed.
Well, thank you. I just want to comment on the size-selective mortality hypothesis, or the critical size critical period hypothesis. I noticed that some of the discussion was on energy and prey quality and prey quantity, and some of the work we've been doing in the Bering Sea on sockeye salmon, juvenile sockeye salmon from Bristol Bay, suggests that at certain times, especially in some years, where there's a lot of quality or quantity of prey, they're doing well, they're growing very well, but the thickness of the prey that they're actually feeding on is quite low, and so that translates into the energetic status of the juvenile salmon prior to winter. In fact, I have a slide tomorrow which I'll show, which is similar to what Dick's talking about, dead fish swimming, is essentially that it's not just size, but you also need to be measuring energy prior to these critical periods for fish.
Great. Thanks, Ed. No? Yes, you're rock.
So my question is a question for Rusty and probably everybody else in the room. So what's the status of the freshwater baseline work? You have to have that first, of course, before you do the ocean.
Not the right start first on it, but just the native.
Freshwater baseline.
Well, for all the salmon that you got in the embargo.
Well, I mean, the status in our lab for the species we're talking about here, exception perhaps of steelhead, is very good. And so we're continually adding more stocks to the baselines and more Washington stocks in particular. In terms of doing this kind of analysis on an individual level for Chinook, it's very, very good. And sockeye, obviously we have less genetic distinction in coho. We do have some genetic stock baselines for steelhead when we're working with the province, but that hasn't been one of our species of most focus. We also now have pink and chum databases as well. So again, the level of differentiation among stocks in those species is much, much lower. So you might get to a basin level, but not, individual streams within basins.
I just want to add on that. For Chinook, Chinook is standardized coastwide baseline, standardized across the board from California all the way up to Alaska. For steelhead in Puget Sound, for Washington, we have good baseline for most of the time. And I guess we're also continuing that in British Columbia. The markers that we've been using for steelhead have been standardized throughout at least Washington, Oregon, and California, although we're switching marker types from one kind to another. The coho right now, for chum, we're in the middle of a fairly large and extensive transboundary standardization that we have samples from Washington and British Columbia. This is funded through Southern Fund with Pacific Salmon Commission, so that's going to be standardized and fairly extensive and comprehensive baseline. Coho has been work also done, as Christy said. We have WDFW standardized our markers with NOAA and with DFO, although there hasn't been a coordinated effort to do a comprehensive work on that, although we do have quite a bit of samples for that. We have nothing on pink in Washington.
All right. Okay. All right, so I have Dave, Christopher, Eric, Tracy, Keith, and Mark. Okay. Dave, you're up. Do you have a mic?
The question came up about the effect of the Strait of Georgia on salmon. And I think it's something that we need to pay a little more attention to, because one of the issues that comes up is the things about climate change. And part of the reason I think the Strait of Georgia, Puget Sound, and the whole Salish Sea is hard to get a handle on sometimes, because it's integrating rate changes which are occurring at different basin scales. One is the North Pacific, so you get these fish which come out and they go out in the North Pacific, and they're integrating the effects of the oceanic changes, where we're measuring things like ENSO and PDO, which has been clearly demonstrated. But when you get down to the level of the Strait of Georgia, then you have things that are changing on annual and interannual bases, and even within the sub-basin, maybe even quicker. And so the frustrating thing, I suspect, in the Strait of Georgia, and maybe this is where we start to go into point number 2 about collaboration, is that a lot of the organizations, governmental, tribal, each university, see things through their little plane of existence. And collaboration is going to mean integrating those different frames of reference, because there are a lot of our difficulty to resolve these things is because we're trying to resolve processes which are overlapped necessarily at different rates. And I think a lot of our success will be generated from being able to develop collaboration, which will help to resolve where those scales of resolution are meaningful.
Great. Hey, can you pass that to this one? Right down. There you go.
This is just a quick question. How to sort of stitch the puzzle together. Modeling and monitoring programs would benefit if we had also information what water masses you sort of catching these fish, and sort of focus certain questions on water masses that we can then help track. So I don't know whether you're sort of taking TS standards with every sort of information piece that you take in order to link everything together, kind of highways in the ocean for salmon, especially also for everyone.
Alright.
Yeah, I want to go back to the acoustic tags again. There's another question. What those that are knowledgeable using them and looking at the results from them, it seems like a really attractive method, but I'm wondering with the size limitations on tags, and what kind of bias there might be, and what willingness to live with that bias we would have to use results for the small tags. So, example, I mean, I know a lot about the Skagit River. You have tags that would work for pretty much all the coho, all the steelhead, but only about 10% or maybe less than that of the Chinook. And what if marine survival results really start at the lower river, like Mara and Correigh suggest? What if we're using these acoustic tags for a direct measure of marine survival? You know, how representative are tags for fish for the population?
Can anyone answer that briefly? I haven't answered that.
We've tagged quite a few fish, considering the Columbia River, between 800 and 1,600 fish per year. And we found that over the size range that we tag, and typically we've had to deal with the same issue in the past when we were using our larger B9 transmitter or B7 transmitter. We have tagged at the upper end of the size distribution. And over the years, using the smaller tags, we've been able to tag a larger proportion of that size distribution. And we have found that early marine survival doesn't vary across the size range. So we haven't found that the larger fish have higher survival all the way along the coast of Washington and up to the northern tip of Lippi Point. So in our case, we haven't seen the size selective mortality occurring in the size range that we've tagged. And in recent years, we were able to tag up to 70% of the size distribution. That's just an example of how there may or may not be a large difference in the early marine survival of your larger fish. Not only size distribution.
Correigh, would you have some more data?
I'll just add that.
That one is 100%. Yeah?
I would just add.
Here we go.
Yes.
I just add that is probably not one method that serves all species of fish. And so if there's a significant component of the cohort that occurs at very small size in the marine system, then you probably don't want to use a physics magnet for that species measure marine survival.
Is there anyone in this room that doubts whether we're getting really poor survival or Chilko cohort in the state of Georgia and Puget Sound? Anyone? Well, if there's no one, I mean, obviously there'll be some population-specific differences, but if we're seeing dismal marine survival and it's been declining, there's a possibility that we see a regime shift and it might change. But I mean, this is something that is one of the few things that we probably can agree on.
Okay. Jason is next.
So I want to go back a little bit to the issue of condition factor and the energetics that was brought up in the middle of the room a few minutes ago. One of the slides I saw in the kaleidoscope go by up there, I think it was in your Rusty, in your 5-minute vignette. It says no significant effects between condition factor and survival. Was that hatchery fish, or was that wild fish, or what was that? So if you broke good, I mean, hatchery fish are going to have much higher CF, but wild fish, but at least in the Columbia, but wild, generally the better fish will have a higher body content and a higher lipid content. So in the Columbia, I think,
Then they come out, we're getting them.
part of it hasn't been fed for a while. Okay, so anyway, that's one that I think the dogma is the condition factor should be related to survival, and if the factor in data says it's not, that's something to track down.
Why if most of those fish are going to die? So if they were swimming dead fish, right? So you could interpret what Rusty says by saying most of them are, very few are going to survive. So the percent that he would measure that are going to survive would be very small.
And I've got Pete and then Mark, and then we can move to our next question.
Just something that popped out at me as we were watching the kaleidoscope go by was that a lot of relationships that seemed pretty good in the 70s and 80s disappeared in the 90s. So one question is have they reappeared since then? And it's not just true in the Salish Sea, it's also true in Oregon and the ocean. And so it's probably related to some bigger scale factors. And one observation is that it's probably a natural experiment that we could use. And one question that occurs to me, are there some relationships that were really good in the 90s that were lousy in the 70s and 80s?
Great. Mark.
I just wanted to make 2 points. The first one, just after a comment that Tracy made. You have to be careful with condition factors. In coal and chinook, they're a very poor indicator of fat and energy, except at the extreme range of the condition factors. When you have extremely low condition factors, extremely high, yes, it's an indicator of fat. But somewhere in the middle, it's a very poor, and it's published that in 2005. So that's documented. But the other thing that's crossed my mind too is something that came out of Michael Schmidt's presentation. And one of the comments made is something like different factors affect smaller species and populations in different ways, although shared drivers across species and populations exist. And I think one of the first things that can be done easily to determine the scale at which you need to look at these things here, like this was mentioned in Symptoms Decline, and Dave was talking about the scale of various scales of response, is just to see how much correlation do you have in the survival of the different stocks that you have within the Puget Sound or Salish Sea area. And if there's a very strong positive correlation between the two, then maybe that would indicate that the scale at which you have to look at these things here is within the deeper waters of this strait, or sorry, the Salish Sea, as opposed to going to individual estuaries or something like this here. So there's a lot of interest, and I divide this world into the splitters and the lumpers. And the splitters tend to try to go into very fine details, and the lumpers, like myself, tend to try to aggregate different things. And you probably have to reach somewhere a compromise between the two different views by looking at the scale of aggregation as necessary to understand what's going on here, rather than trying to necessarily go to either extreme.
Right? Thank you.
Yeah, so I agree, and that's part of what Correigh and I were proposing to do, is to do that spatial comparison in areas that we have solid smolt and adult estimates from. In Puget Sound right now, there are areas in the early 2000s that we have higher coastal marine survival than we did in the 70s and 80s, and there are areas where it's gone the other way. So there's opportunity to do exactly that.
All right, so we should move on, I think, to our next question, which is where is U.S.-Canada collaboration most valuable? Among these hypotheses and research recommendations, where should we be working across the border? What's your thoughts on that? Comfort? And Dave? That one you might have to set really close to. Use the function.
So one thing that comes to mind immediately is that all the work that has been conducted by DFO coming down with the Ricker over the past decade has been essentially gratis. It's been very good. Their willingness to provide that information, and yet it's a really critical part of the information that we've been able to grab to date. And so I would say, that's sort of created a backbone that we need to build off of and supplement and hope it doesn't go away. So a lot of gratitude from the southern neighbors to our Canadian friends here.
Great. Seconded? All right. Good. Thoughts on where U.S.-Canada collaboration might be valuable?
Again, I guess my bias is towards primary productivity at this point, limitations, but it seems like we not only need to tie Salish sea productivity to the components north and south, but also to what's happening in the ocean. And it seems like maybe I'm not a primary productivity person. We have a little better information in the ocean than we do in the Salish sea, and so it seems like when we have Bill Peterson and the DFO folks already running transects, it would be good to tie that all together, and that would be a collaborative effort.
Great, thank you.
And I think Puget Sound is far ahead of us in that level.
Well, one place for collaboration that's spatially obvious is South Strait of Georgia, what I call North Puget Sound. The Salmon Islands and the bays around Bellingham and of course, that area is very closely tied, both biologically and geologically.
Yeah. So safely. All right. Other thoughts? Yes.
Well, I think one that comes obvious to me is the availability of data across the border. I think a joint data management function where we actually, if we went to do, say, meta-analysis of a number of studies, it would be nice if it were even a function where you have links to various people's data, and that would allow, I think, studies that wouldn't necessarily just stop at the border, as some of them even do now, but we would be able to more easily look across and amalgamate results from studies both in the U.S. and in Canada.
Other thoughts? More?
I was just going to say, I think the genetic databases that are joined for U.S. and Canada are essential to understand what's going on. And we've learned that in the ocean for the stuff off Washington, Oregon, goes all the way up to California, or Alaska. You have to know where your fish is coming from to extent of it. And by having everybody in the same country on the genetic data and sharing samples, that's the only way you can do it. So it's very important.
Very cool. Thank you. Okay. Carrie? I look at it.
I'm just wondering about, in looking at where we're headed,
with understanding of fishery survival and productivity, how we can do a better job of incorporating habitat data along with fish data. It seems to me that our fish data over time is fraying because of all the different issues you're speaking to. In some of those areas that where they're fraying, if we could see what's going on in the habitat at the same time, to see if there's any indicators there that might help us look at what other types of issues we might want to focus on.
Okay. Last call for this one? No.
I think one of the key things is where we always slow down things like this is and come up with great ideas and programs for monitoring and doing science, but it doesn't go anywhere unless you find money. So I think hopefully down the road here soon, maybe with specific standard commission funding, tree funding up, I think having those signs at the border agreeing that this is a priority, putting together collaborative proposals from both sides, I think would be key. And then also to our individual access for funding either side of the border too. For example, for us, for BC Hydro and that, again, having everybody agree that this is a priority that we want to pursue, everybody focusing on that.
Great. Okay. All right. We'll spend a few minutes on resources that we could take advantage of that haven't been mentioned already. So we're talking about vessels, we're talking about labs, we're talking about collaborators, all kinds of people. Ed?
Well, maybe most of you don't know me. I'm Ed Farley from the great country of Alaska. And I don't know if anyone else is here from Alaska, but maybe most of you know that the Chinook salmon returns to Alaska this year were down statewide. It's a big state, so that was a big concern. There are a lot of areas that were labeled disaster areas, and so the Department of Fish and Game put together a group of panelists and scientists 2 weeks ago to come up with what we know about Chinook salmon and what we don't know, a gap analysis. So there's a lot of information that was at this meeting. There were about 300 people there. There were the sessions sounded just like what we're going through here, and a lot of the topics that came up there were similar to what you're discussing here. Marine environment, freshwater, genetic diversity was one of them. I know that when the hatchery and other groups got up there to talk about genetic diversity, there was the wild stock survival of around 3%, and the hatcheries around 1.5%. So there's issues there potentially with genetic diversity, and that was discussed. So I would just recommend looking towards the Department of Fish and Game. Eric Volk is leading this, and there will be quite a bit of information coming out of that 2-day workshop.
All right. Thanks, Ed.
Hey, Ed, tell Eric to call me then. Email him already.
Okay. So Josh, and then you guys, I mean, you can arm wrestle, but Chris and then Mark. Josh, you have it.
Yeah, okay, so the question I want to ask is, we had some presentations on data that was being collected on fish populations and taking the fish perspective. Are there activities that are going on or analyses that are being done routinely in Canada that are not being done in the U.S. and vice versa? And should there be some economy of scale by carrying out joint work or one particular specialty in the U.S. that should be done in both U.S. and Canada and vice versa?
Does anyone have a quick response to that, or? Okay. Chris? You don't have a response. Does anyone have one?
I do.
Jacob?
Yeah, I think a fair amount of the work's been done both in U.S. and Canada, again, using river data. It provides a common data set. It lends itself to doing common analytical methods, and I think there's a wide open opportunity to do a fair amount of that. We just haven't had the resources to really mount that to date so far. And I would add to that, Chris is talking tomorrow, but everything that he's going to talk about, we can do it on. We just don't have the ability or the technology to do it yet, but it's important to talk.
Okay, thanks. And then Chris, you're going to respond to that.
That was sort of my addition. One of the things that we're doing in Canada, and I don't believe any labs are doing yet in the U.S. on at least the kind of scale that we are, is using functional genomics technologies to look at genome-wide physiology of these fish And we have a 4-year program where we've been looking at out-migrating from the Fraser River largely of Chinook coho and sockeye salmon, and looking at how the physiology of the fish varies both over migration and between different years and among fish in the same common rearing environment. So trying to use this technology to begin to tease out what kinds of stressors those fish are under in different environments. So I'll talk a tiny bit about it tomorrow, but anyway, that's something if anyone's interested in talking about, I'd be happy to.
Great. Okay. Actually, can you contact that first? Oh, sure, we have some. Another initiative that's in BC right now is the Southern BC Chinook Salmon Technical Committee, and they're taking a look at what has happened to Southern BC Chinook salmon. Kind of these same topics where the bottlenecks, it's right from freshwater through the marine, and so this is just going on at the same time. Something else that we need to be able to do is share our data. So we've been working with people in Puget Sound for some time, but we have a lot of information on early marine fish, such as CWTs, DNA work, and we cover a lot of U.S. fish in the state of Georgia. And the current databases and structure for uploading that information isn't available for juvenile fish. So making sure that we are communicating, and the people working on those stocks in the U.S. that we may be catching are aware of the fish that are utilized in the state of Georgia. That's important. Great. So better data management and sharing about it. Mark?
So, I guess this is a topic that will be covered tomorrow, but there are other long-term research monitoring programs that have been going up and down the coast. And I think from a hypothesis testing point of view, it's worth trying to tap into what these programs have done. And especially when you're trying to do contrast between different treatments, having samples coming from different ocean domains is one way of increasing the contrast in your independent variables. If you do see differences in the response, at least you can find some ways of eliminating some hypotheses. But you should also be aware that some of these programs are currently at major risk of disappearing given some major funding shortfalls for these programs.
Thanks. All right. Kristen, did you want to chip into that? Yeah. One thing that I'd like to stress is from economic data, one of the things that we are observing both in return migrating adults and out migrating smoke is that a lot of the main physiological variables that are differentiating fish on a migration trajectory are common, and these are the ones that have the largest signatures, are common among freshwater and marine environments. And although the prevalence of these different signatures seems to oftentimes vary over time and space, we're kind of, with the analysis we've done so far, formulating a hypothesis that the condition of the fish that are leaving the river may be almost as important as the conditions in the ocean. And so I think we should be careful as we develop programs moving forward not to or at least to set ourselves up to be able to look at what was the condition of those fish when they left the river as well, and looking at how that might change over time and space. Oh, Correigh, do you want to?
Yeah, I just wanted to respond to that real quick. I haven't heard a lot about the Canadian efforts for out-migrant trapping, but I'm just curious how often, or the spatial extent of that, we simply highlighted on the Puget Sound side. And so I think your point's well taken that we really do need to focus on the condition of fish going out.
Chris, did you have a response to that?
I can't comment on all the rivers in BC, but I know in the Fraser River this year, because of that issue and not knowing the condition, there is a track set up to monitor downstream migrating Pink salmon at Mission, and we equipped that with rotary through track to also take a look at Chinook and sockeye salmon, and hopefully we're going to be continuing that. That was funded for the Pacific Salmon Commission.
Okay.
And I just want to add, project and other very few stocks for which the monitors smoke up migration for coho in the Salish and outside the Salish. It's very
Thank you. Brian, you had something to say, and then we need to move to our last question and then save time for observer questions and comments.
Okay, but just real quick then, I think one of the things that we should immediately share, and Isabel and I have been working on this for a little while, is getting a comprehensive inventory of researchers and lab capacities, vessel availability, community groups that can contribute to our science, observational or even in doing direct sort of a network of science programs and sampling and that. So I think there's a lot of capacity out there, and the trick is really learning who's doing what in that event, because there are so many different agencies. So even if we can accomplish an inventory that we can really rely on, I think that'd be invaluable to start. And a few people are testing on the data that we have for true assessments, and I think we're going to have to tackle that as one of the major tasks if we proceed on collaboration like this.
Thanks, Brian. So I have Kurt and Richard. He said no. Okay, Richard, my one. Okay. That's okay. Yeah. And then we'll open the floor for observer comments, and we'll address that fourth question as part of that.
I just wanted to open up, make this a little broader. There's a lot of talk about the early marine survival, but there's the back end of the life cycle as well that maybe shouldn't be completely ignored. That's the returning adults. And I think we should be aware that as maybe climate change or these big systems change the timing, if, for example, this year was a good example when the rivers were not flowing and they were at their lowest levels right through September and October, this could help that returning stock in future years. So there's the returning side of the equation as well that maybe shouldn't be completely ignored.
Don't forget the adults, they're important too. Okay, thanks. And I want to thank the observers for being very patient. Ramona, you had a question or a comment earlier?
Yeah, first of all, I'd like to thank the tribe in the traditional territory to meet today. Number one, I'm wondering about Ron's massive work with the fossil studies of Barking Sound and how instrumental that's been to help us inform what we're doing there, and if that could be duplicated in Puget Sound, looking at the fossils and his analysis and his modeling technique, because getting more data around that I think is really instrumental towards prey and predators. Also, there are things we aren't using the First Nations data sets. In British Columbia, I think are highly underutilized, and it's something we have to change, especially when we start to look at forage fish issues. And lessons and opportunities for other work. There's a group of fish in Southbound Salmonidae called the Osmeras, and they are collapsing. And these are the oolacans, the first melt, and the longfin. And I think a salmon strategy like this could benefit and provide an opportunity to look at why they're also in trouble. And maybe studying that a bit might help us get more funding. And it's going to help, I think, overall look at the forage fish part as well. So under your opportunities with the salmon, whatever you think about looking at the prey and other research initiatives, don't forget that there's another group of fish that are also in a rapid decline in these waters and maybe create some relief.
Thank you.
Thank you. I have some feedback on hypotheses and research recommendations, which is number one. Number four talks about diversity among salmonids populations conferring stability. Ken's presentation focused on genetic diversity, but I heard a little bit of discussion here and there of life history diversity, but I think life history diversity should be a focus also, at least as a hypothesis. We have also the last presentations were basically on trawling information, which tells you that those fish caught are going to be eating marine plankton. But we know that juvenile salmon, at least in Puget Sound and probably throughout the Salish Sea, eat terrestrially derived food as well. But I don't know how important that is. But I think there's diversity of life history strategies. We have resident fish, we have fish that go right out to the ocean, and those life history diversities happen between populations, and they also happen within populations. And I think at least it's possible that that stuff is important. So I urge you to include that in your hypotheses.
Thanks, Ken. Other comments or questions?
I can say a little bit about the terrestrial. In Chinook, we do find
In certain areas, we do find a larger load of winged insects, usually like termites and ants. Tends to be in relatively narrow channels where they're flying across and they get caught up on the surface or something. But in the more open water, say in the Strait of Georgia more commonly, we rarely see any kind of terrestrial insects.
Correigh, did you want to respond?
Yeah, I definitely agree. Life history diversity is a pretty important component, and I think from a research project that spans 5 years, it's probably going to be difficult to detect a life history variability in that time period that confers advantages on a larger community scale. That said, I think there are signals in some of the presentations that have been made which illustrate the importance of life history diversity. For example, there's a pink salmon, Chinook salmon pattern, which is readily observable in hatchery fish, but is not often observable in wild fish populations. And that's probably a reflection of the variability in residency within tidal delta and nearshore environments.
Jacob, do you want to respond? And then Ken and I got 2 more comments back here. So.
Yeah, we're seeing the same thing in Puget Sound as Rusty is seeing up in the Strait of Georgia. There is a pretty strong signal of terrestrial insect input. They're very important with Chinook, and it turns out some of the other salmon as well. We also see a bit of a regional trend in the importance of those fish among different subbasins within Puget Sound. I'll show you a little teaser of that in the next session here.
And I would like to add, too, that we also should probably understand the interplay between genetics and the environment and life history diversity as well.
Sort of related to the diversity question, it was interesting in the portfolio presentation that the early run fish had preserved their diversity, but it actually crashed much more dramatically than the hatchery influenced fish. And I think it said that the early run fish actually made 50% of the production out of that area at one time. I think that conversation was happening in the Southern BC Chinook meeting a week ago, that, in a lot of these systems, the early run fish actually made up, 50% or more of the population, and some of those were probably stream type fish. And I know we've talked about that a little bit, but it seems that those fish have had a much more dramatic crash, and whether there's something there to do with that.
Thanks.
This is on the topic of whether or not steelheads are preying on those acoustically tagged fish. I'm just curious, for those of you who have been doing that work with the steelheads, is there any thought of putting fish tag scanners on seals and sea lions as a potential way of avoiding the issues with the acoustic tags?
You want to respond to that? Okay. All right, any other thoughts or questions? Any other questions? All right. Well, speaking of the dinner bell hypothesis, it is lunchtime. So please come back at 1:30. Thank you very, very much.